Okay, we'll look at in-class exercise 3 on the bond-Haber cycle for beryllium oxides. Okay, so as usual, the data given to us, I mean, not too surprising. We are given the enthalpy change of formation of beryllium oxides, and then the atomization of the elements beryllium. You also notice that you are not given the atomization for oxygen, but I think that's quite obvious why you are not given, because you can easily find the bond energy data from the data booklet and determine the atomization enthalpy from there. Okay, so I guess the very first thing we need to do is to draw the zero line. Okay, and in the process incorporates the elements there. So in this case, beryllium solids. Okay, plus half oxygen gas. Okay, and here we define the enthalpy change of formation. So this is the enthalpy change of formation we define. So this is BEO. Okay, of course it's a good habit to copy the values over. So it's negative 609. I'm going to use another color, negative 609. Okay, and remember that the first step is to write down the definition for the enthalpy change of formation. And because we are given that it's exothermic, so we point the arrow down. The next thing we want to draw in here is likely to be the lattice energy definition. So from the lattice energy definition, so this is what we really want to find. So this lattice energy of BEO. It's being defined as a gaseous ion, so this Be2 plus gaseous plus O2 minus gaseous. Okay, yep. And as per what we have always been discussing, we need to go from the elemental states all the way to the gaseous ions. Okay, so we need to make use of the information to go there. Right, so I'm just going to erase this first. Okay, so since we are given the atomization enthalpy, so we might as well just make use of this information. So first we incorporate the atomization enthalpy in. So we'll be doing the enthalpy change of atomization for solid beryllium. It's given to us as 324. So we're going to get beryllium gaseous, and we are from the data booklet, we can also find out the bond energy of dioxygen molecule. So that's 496. So because we only need one equivalent of gaseous oxygen over here, so therefore we divide that value by 2. Okay, so so we will expect this to be 324 plus 496 divided by 2. Okay, so over here we define the enthalpy change of atomization for beryllium, as well as half bond energy of oxygen over here. Okay, then the next thing we need to do is to flip over the data booklet and determine the first and second IE of beryllium. And remember that for similar energetic terms, we can actually combine the values so that we do not need to draw so many levels. Okay, so in this case, we'll combine the values. So we just go up here. So that's this will actually give us Be2 plus gaseous plus 2 electrons. Okay, plus oxygen gaseous. Okay, so this value is found to be flip over is 900. That's the first IE, and then 1760. That's the second IE. Okay, then after that we go down because that's you are given the first electron affinity of oxygen, and then after you are given the second electron affinity of oxygen. Okay, if you want, you can sum them up. Negative 141 plus 798. That will give us 657. But of course, over here, because we are practicing drawing of bond-Haber cycle, so I think it's good to actually just to draw them out separately. Okay, to check on our mistakes. Okay, so that's that will give us Be2 plus gaseous plus electrons plus O minus gaseous. Okay, then after that we move out again. Okay, so we're going to put in the values here. So this will give us negative 141, and 798. Okay, so do we get a complete cycle? Let's try to use the yellow line to trace. So from here we go up, and then we go down, we go up, and we go down, go back to this point, and then we can go up again. So this is a complete cycle. Okay, so yeah, so everything's good. Now let us use Hess law, okay, to sum everything up. So there are several ways you can go about doing that. I think the easiest way we want to do it would be, okay, this is our destination, starting point, from here all the way down. Okay, so since this is starting point, we'll just go down here, up, and then down, down, down to reach our destination. So we'll go from here all the way to here. But we cannot go down directly because there is no route. Or rather, this is what we're going to find. So we have to go by an alternative route. That is down, up, and then down all the way. So remember, if you are going against the direction of the arrow, then you have to switch the sign. Okay, so therefore, lattice energy in this case is equals to negative 798. Okay, plus 141, negative 900, negative 1760, negative 324, negative 496 over 2, negative 609. Okay, so this will give us a comfortable negative 4498 kilojoules per mole. Yeah, so this is one way we can do it. Okay, if you are comfortable in going by this route. There's also another way, but again, as I said, all roads leads to Rome, so you don't have to fix one method of doing. Some people prefer to start from the 0 point, so in this case, the elemental state, and then they define going from here to here. So you can do that as well. So that's negative 609, and then you just go up, down, up, and then down. Yep, that is not a problem as well. So negative 609 is equals to 324 plus 496 divided by 2 plus 900 plus 1760 minus 141 plus 798 plus lattice energy. Okay, but you realize that we are actually doing the same thing, because after you have done this, you're going to make lattice energy the subject, and then you're going to shift all the term over to the other side. So all these will go over the other side. You notice that when all these terms goes over the other side, you end up with the same outcome. Okay, so 3 to 4 become minus. So you see, it's minus here. This become minus, minus here, minus, minus here, minus, minus here. And then 1, 4 will be plus, so it's plus here. Then 7, 9 will be minus. Yeah, so all road leads to Rome. So you get the same answer, negative 4498 kilojoules per mole. Okay, and the next part is the theoretical lattice energy of beryllium oxide is given to be minus 4432. Suggests the reason why this is the case. Okay, so again, how do we calculate the theoretical lattice energy? We assume that Be2 plus and O2 minus assume they are point charges. Point charges. Okay, of course, in reality, they are not point charges, because in reality, beryllium 2 plus has high charge density. So that means that it's able to polarize the O2 minus electron cloud, okay, to a relatively large extent. Okay, then what's going to happen to this? This will give it a partial covalence character, which is of course not accounted for by the pure ionic model. Okay, so that explains why there's a difference between the two values.